All right, 6.3, pretty large section. This is definitely the meat of the chapter. So, what we've been talking about for the first two sections, in section 1, we kind of just defined for the first time what is a random variable, and in section 2, we kind of talked about how to multiply constants, add constants, and to combine random variables. In section 3, we talk about special random variables. And really, we just talk about two of them. The first special random variable is the binomial random variable. It is a very special discrete random variable. It is a discrete random variable, which means it takes set outcomes. So, when the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. So let's build what makes a discrete random variable a binomial random variable. So we have what's called the binomial setting. So the requirements needed. We call these the requirements needed in order to say something is binomial. It's called conditions. So a binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The four conditions are binary. The possible outcomes of each trial are classified as success or failure. So no matter what it is, if you say it can be success or failure. Independent. Every trial must be independent of the next one, meaning knowing the outcome of one does not affect the outcome of the next. N is for number, but what it means is the number of trials is fixed. So you have a fixed number of trials in the whole kind of setting you're creating. And then the probability of a success can never change. The probability is the same probability of a success each trial. And you'll notice the first letters are highlighted because BINS is our new acronym. We've had SOX, we've had CUS, we've had FODS, and now we have BINS. BINS is for creating the binomial setting. And I will be upfront with you. You will have to know how to create this. So you won't be able to just take a problem, get the answer. You will have to establish binomial setting in order to use binomial probability. So let's take a look. Two examples real quick. A manufacturer produces a large number of toasters. From past experience, the manufacturer knows 2% are defective. The quality control procedure, we randomly select 20. We want to determine the probability that no more than one of these toasters is defective. All right. So we know our fixed probability here from the start is that 2% are defective. We have our fixed number of trials, and it's that 20 toasters are in the test. Independent. We have the independent because it says a manufacturer produces a large number of toasters. So let's say that one toaster's ability to work is not affected on the next toaster's ability to work. Meaning we're not thinking like, oh, maybe the assembly line went wrong for 10 minutes. Because there's so many toasters to choose from, we're saying that each toaster is independent from the next. Which means the last thing is, do we have a success or failure here? Yes, we have just success or failure in that toaster is defective or not defective. So yes, first one is indeed a binomial setting, and we would be able to use our new binomial random variables. Why is it different from the second one? Draw a card from a standard deck of playing cards. Observe the card and replace the card. Okay, so we're drawing a card. We are replacing it, so we have independence. Count the number of times you draw a card in this manner until you observe a jack. So this is counting, this is picking card, putting it back, picking card, putting it back until you get a jack. Well, that means we don't have a fixed number of trials, letter N in our bins. We do not meet that, so not binomial. So that's why when you start these questions, it's very important to understand, do you indeed have a binomial random variable? So we have from a binomial random variable, we create binomial distributions. So let's take a look. Consider tossing a coin n times. Each toss gives either a heads or tails. Knowing the outcome of one coin toss does not affect or change the probability of the outcome of the next. So we have independent, we have binary. If we define heads as a success, so there's our situation. P is the probability of a heads is 0.5, or it's a fixed probability each time. So we have binary, independent. We're going to get to our fixed number of trials, and then we have fixed probability. The number of heads in n tosses is a binomial random variable. So basically, I have the outcomes possible if I say I'm doing 6 flips. I have the outcomes possible if I'm saying I'm doing 9 flips. That each one of those is a binomial random variable. We also have what's called the distribution. The probability distribution of x is called a binomial distribution, meaning you can look at many different trials, and create a full binomial distribution. So, what are the outcomes if I flip 1 coin? What are the outcomes possible if I flip 2? What are the outcomes possible if I flip 3? Creates the distribution of all of the outcomes of the event. So the count x of successes of a binomial setting is a binomial random variable. So like 4 heads, 5 heads. The probability distribution of x is a binomial distribution with parameter, fixed sample, and fixed probability, where n is the number of trials and p is the probability of success each time. The possible values of x are all the numbers in 0 to n. So this is saying 1 success, 2 success, 3 success, 4 success, 5 success, up to n successes. Creates the whole distribution. That's just vocabulary. Now let's see how you do it. So if you know something's binomial, why is it better? In a binomial setting, we can define a random variable, say, again, x is a random variable, as the number of successes of n independent trials. We're interested in finding the probability distribution. Here's our example. Each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics says that children receive genes from each of their parents, boom, perfect, independently. If these parents have 5 children, sample size, the count x of children with type O blood is binomial random variable with fixed number of trials, 5. Fixed probability of a success, 25. Independence, yes, it is stated. Binary. It is binary. Now, you're all probably thinking, yeah, but there's a lot of different types of blood. Type A, type B, type AB, type O. But this is binomial because a success, okay, is just a child with type O blood. See right here. Probability 0.25 is success of each trial. In this setting, a child with type O blood is a success. So it's okay there are different types of blood, but all of the rest are just considered failure. That creates binary. Okay, and a child with another blood type is a failure. We want to know first, how do I get the probability that exactly 2 of the 5 kids will have type O blood? So let's think. The probability would be a person with type O blood, 25%, and from last chapter, right? That's why this comes right after probability, and type O blood. Independence just says multiply, and not type O blood, and not type O blood, and not type O blood. So I have 2 successes, so probability of success raised to the second for the 2 successes. Probability of failure raised to the third for the 3 failures. And what you should be saying to me right now is there's a giant red flag. Because you're saying to me, well, Mr. V, when we learned probability at the beginning of the year, and when we learned probability last chapter, what about all of the orders that this could occur in? There absolutely is 5 choose 2 ways. 5 choose 2 ways of ordering 2 successes and 3 failures. Look, I've written them out. 5 choose 2 is 10. So what do we need to add? We need to add the 10 ways that this could happen. 2 successes, 3 failures, to get all the proper arrangements. So the real probability of getting exactly 2 out of 5 type O blood is a binomial situation. So let's see. You've maybe seen this before. You've all seen combinations before. But believe it or not, this is just using the idea of what a combination is, n factorial over k factorial times n minus k factorial. So this is a combinations question where you have the combinations the event can happen times the probability of a success raised to how many successes times the probability of a failure raised to how many failures. This is called the binomial coefficient, but it is as simple as just a combination, n choose k. So in summary, a binomial formula is the probability of a success raised to how many successes you want times the probability of a failure times how many failures you need, and then all of the ways of arranging those is n choose k. It's all of the combinations of the same two things. And that is how you can get your probability. Number of arrangements, success, failure, and however many you need to raise it to. So here is going to be our method for solving binomial probabilities problems. First, state the distribution and values of interest. Specify a binomial distribution with the number of trials, the success probability, and the value of the variable that you actually want, like 2 successes, 3 successes. Then perform the calculations and show work. So what we could do is use the binomial probability formula, or, which you know is probably coming, we're going to use a calculator which has built-in binomial PDF and binomial CDF commands that we will utilize both of them. Lastly, answer the question of interest. Make sure you let them know the probability of getting 2 kids with type O blood is 26%. All right, same generic problem. Now we're going to see exactly how it works by formula, which I hope you never use, and we're going to see how it works with calculator, which I hope you do use. Each child of a particular pair of parents has probability 0.25 of having type O blood. Suppose 5 children, same binomial setting. Find the probability that exactly 3 of these children have type O blood. Piece of cake. Formula says, let X be the number of children with type O blood. Identify the variable. X has a binomial distribution with n equals 5, p of 0.25. If I want the successes to be exactly 3, meaning the random variable takes 3 successes, it's 5 choose 3, success cubed, failure squared. That is great. I will stop. I will show you how in the calculator we can do this as well. So what you're going to do is you can pull up your calculator. It's the same place we had normal CDF and stuff like that. It's in your distributions. You will indeed have to scroll down to binomial PDF. Right now it's PDF. It says how many trials are there? Well, we had 5 kids. What is your probability of a success? It is 0.25. And then how many successes do you want? I want 3 of them. And you get your answer. Well, it puts it in there, and then you get your answer of 8.7% chance. Now, with normal CDF, we had to label our work. We do have to do that as well here. You have to say this is binom PDF, and you would say 5, 0.25, 3. And you would have to label your work to get work credit. You would say trials. You would say probability of a success, which is our p-value. And then this is our number of successes. So this would be number of successes. Trials, n. Probability, p. Number of successes, 3. Label your work. And now again, what happened here? When I wanted exactly a number, meaning exactly 3 successes, it was binomial PDF. Let's go back to the slides and see how it's a little different right here. So I won't pull it up. Right here. So what happens in our next one? Should the parents be surprised if more than 3 of their children have type O blood? Well, now it's not exactly something. Now it says more than 3. What does that mean? That means 4 or 5. Probability says when things are or, you add them. So I find the binomial answer for 4, type O. I find the binomial answer for 5, type O, and add them together. Well, the calculator can do that as well, but we can use the binomial CDF function to get cumulative probabilities. But there's a small catch. Yes, there's still 5 trials. Yes, the p-value is still 0.25. The x value is where it's blinking right now, is where you have to think very importantly. This will cumulate the probability from 0 up to and including the probability of the value of the trial you say stop. So what it's doing is a PDF at 0 plus a PDF at x value 1 plus a PDF at 2 plus ... no matter where, and it stops on where you say stop. So if you set a binomial CDF to 3, let's say, it would do these 4 probabilities and add them together for you. It's the only way it works, is it does 0 plus 1 plus 2 plus up to and including the one you say stop. Well, I purposely put 3 here because if you're thinking about 5 children and them having type O blood, if you really think about it, the amount of kids that can have type O blood are 0, 1, 2, 3 of them, 4 of them, or 5 of them. So if I want 4 or 5, doesn't that just mean I don't want the stuff in the box? I don't want 1, 2, 3, or 3. So if I put 3 in here, this is going to give me the probability of having 0, 1, 2, or 3 kids with type O blood. What can I do with that? 1 minus the answer. And that will give me my 0156. It'll give me the rest, because this one did 0 plus 1 plus 2 plus 3. This took 1 minus that to give me the rest, 4 or 5. So binomial PDF gives you an exact answer. Binomial CDF gives you a cumulative from 0 till you and including the one you say stop. So 0, 1, 2, 3. So you have to be pretty careful in questions like this that it says something like more than or equal to, greater than or equal to, less than or equal to. You have to be careful of that. So moral of the story here, binomial PDF when you have an exact x value. Binomial CDF helps you when you want to find a range of answers. And always keep in mind, it starts counting at 0. So use your 1 minus 2 if you need. Last question of today. Suppose that James guesses each question on a 50-item true-false quiz. So let's make sure this is binary. Let's make sure this is indeed binary. What'd I do here? Try again. It's binary because it's true or false. Okay. It's binary because it's true or false, so success, failure. It is independent because suppose that James gets on each question 50 true, find the probability of James if the score 25. It's independent because one question doesn't affect the next. Doesn't affect the next. 50 questions, number of successes on true false will be 50% for guessing. So it fits all the needs of being binomial. Okay, what is the probability that he passes if a score of 25 or more. Different. Not more than 25. 25 or more is needed to pass. So I could do a binomial PDF of 25, 26, 27, 28, 29, 30, 31, 32, all the way to 50 and add them together. Terrible decision. What I could do is a binomial CDF. Trials is 50, fixed probability is 0.5. Label it trials. Fixed probability is my p-value. And then how many successes am I looking for? Well, if I want 25 or more correct, that would mean I want to get rid of up to 24 correct. And I could do 1 minus this to leave me with 25 or more. If I get rid of, okay, that will be successes. If I get rid of 0 through 24 successes, it'll leave me with all of the probability for 25 or more. So let's go to the calculator and let's put that in. Okay, 1 minus, you can do this before or after. Distributions, binomial CDF. We now have 50 question multiple choice, true false, 0.5 probability. We want to get rid of the first 24. Paste, enter, 55%. So answer the question. There's a 55% probability he guesses correctly. Again, there is a 50, I don't know, it's not writing. Make sure you answer the question. There is a 55% probability that he answers, or 56% probability that he answers, passes the test, meaning guesses over 50% correct. Okay. Now, binomial CDF will not always be 1 minus. Keep that in mind. If I said, what is the probability on this question? It wasn't more than 3 children, and it was less than 3 children. Just don't do the 1 minus. So binomial PDF, binomial CDF, and always keep in mind how to answer these questions, and you must establish the binomial setting to use this. That's the first half of 6-3. See ya.